All right, let's get this show on the road. All right, so chapter 4. All right, we might as well go in order. So chapter 4 are how comfortable are you guys with IUPAC? It'd be good if you guys can give me some sort of insight. Chapter 4. Pretty good. Really good. Let's see. So I'm assuming by really good, you guys know exactly what to do, at least 95%. All right, struggling with chairs. All right, so there is the possibility for you guys to see a Newman projection of a chair. Have you guys seen that before at all? A Newman projection of a chair. All right, so let me pull this up. Newman projection of a chair. All right, so feedback. All right, Newman projection of a chair. I've seen it before. If he's never shown it in lecture or ever even mentioned it, it's probably safe to not do it, but I don't want to, be that TA that, doesn't cover something and has it come up on the test. Because then I have 50 emails saying, oh, you said it wouldn't come up on the test. And yeah. All right. So we all know chairs look like a chair. Right. And also, if you're not a student of mine, just know that I don't have a tablet. So pardon my drawings because I'm using a mouse and on a bed. All right, so that was sucky. All right, a chair. All right. Now, just a what a double chair is, it's like a double Newman. It's not a double chair, it's a double Newman. All right, because if you, a chair to a Newman, you're looking at two carbons, this one and this one. So your mind's eye is doing this. All right, so it's no different than looking down a butane, but you're just looking down two bonds. All right, so you have two front carbons and two back carbons. All right, so these in blue are your front carbons. All right, and what's coming down from those two carbons? What is this? What's coming down from the two carbons? CH2, right? So here's your let's just say left front carbon, and here's your right front carbon. Coming down from it, it's going to look like this. All right, and this is your CH2. That's at the bottom corner of the chair. All right, so if I'm looking at this, right, let me just maybe use my head as an example. So here's my fists are the two front carbons, right? Coming down from them and connecting is my head, the CH2. All right. And so what is coming off? What else is on this first carbon here that I circled? What else is on it? Dustin says a hydrogen. How many? It's just a CH2, right? So just fill in. These are your two hydrogens. Now this side here is the same thing. So fill in. All right, now you have these back carbons in red, right? These back carbons in red. All right. Something's coming up from them and meeting like this. What is it?
Could you say that again?
So from these back carbons, if you're looking down this way, if you're looking down this bond, right? You're looking down this bond, there's this top corner of the chair, right? What is that?
Carbon with two H's.
Yeah, it's a CH2. So how that's going to look is like this, all right? So here, this CH2 is this corner that I arrowed in blue, and this CH2 is just that corner. All right. So there are two other groups coming off of each of these. This seems really mean for a Newman projection. Yeah, but I've seen it come up on an exam for a couple semesters. I personally got it, and I got it wrong, so I don't want that to be you guys. And these are just CH2s, so fill in. All right. So for a plain cyclohexane chair with no substituents, this is the double Newman for it. All right, that's it. And it does not rotate from this. The front and back carbons do not rotate on this Newman. All right. Now, if I were to throw, say, if I were to do another chair. All right. Now let me put I don't know. Cl here. And the alcohol there. All right. So you know that here, again, just being consistent, here in blue are your front carbons. All right, and here in red are your back carbons. All right, so let me just draw the back carbons first. So the back carbons are your typical circles. All right, now coming up from them and meeting is a what? Is our carbon, right? We have this here that's meeting up there at an angle. And then what's coming off of it? An OH. All right. Now here, now what else is on these front carbons? I mean, what else is on these back carbons? H's. And there's really only two places you can put them, right? Here and here. All right. So the back's done. Front carbon. All right. So the front carbon, there's nothing on this. So the front carbon has this coming down from it, has the CH2, just like the example above. All right, so looking down these bonds, if you're noticing a pattern, this carbon, these in green are going to be the things here. All right. So I would recommend just starting with the base structure here, and you fill in based on axial and equatorial. All right. So looking at these front carbons again, you have this Cl, right? And you have an OH. We need to decide where we're going to place it. Here going up or here going out at this angle. Does anybody have an idea of how to decide that? Yep, it's going to be up. All right. Because again, your vantage point is, again, here. You're looking at it that way, right? So your CH is going to be coming. So if you're looking at something this way, right, you see that the Cl is here, all right, and we see the H is coming inwards and out of the chair. All right, so you guys are right to say that the Cl is here, the H is here. Is there any substituents on this other front carbon? No. So you just fill in with your hydrogens. All right. So again, this is your base structure. So if you're given a Newman, if you're given a chair even with substituents, you can go ahead and draw your base structure and just replace the hydrogens if needed with the substituents. Right? If he's never mentioned this before, neither Chris or Levi, if that's the other SI this semester, it was last semester. Jared was the other. All right. So if Jared or Chris or the professor did not ever mention this, it's likely to not show up. But I've seen it show up before, and so I just wanted to make sure to touch on it. All right. So I'll just go ahead and what question would they ask about it? So it's weird. I don't remember exactly how he asked me personally about it. But he gave me a chair, I believe, or he gave me a name, and he asked me what the Newman projection was for it, in which you should be able to go from the name to the structure, right? So it's no different than just giving a structure and asking you what the chair is or the Newman.
Right. Sorry, can I ask you a question? Do you have a video? Because I didn't know that this was being held, and I just found out about it after you had already started going over it. Is there like a YouTube video or anything that you recommend that I can watch for how you drew that?
Yeah, I actually have, so this is chapter 4. I actually have my chapter 4 solutions that I can put in the chat, and you'd be able to download the file.
Okay, that sounds good.
So that's a double chair. All right. So what else do we see in chapter 4? So we also see, is anybody struggling to decipher like the different conformations in a Newman? So like deciding between partially eclipsed or fully eclipsed, anything like that?
I think eclipsed is easy since it's the same molecules basically touching each other, right, on top of each other, right? So,
yeah, so eclipse is really, I always think of literally the sun and the moon eclipsing, right? So say the sun is your front carbon and that doesn't make sense. The moon is the front carbon and the sun is the back carbon. They literally come in line with each other.
I understand the extremes, like eclipse, and the other one, I forget the name, but the one where the same molecules are as far away from each other as possible. But I don't understand the intermediate part, where it's I think
Gaussian partial.
Yeah, that.
All right, so let me see if I can pull up my stuff. So let me switch docs. Right. So here's a good example. You've probably seen this actually come up on your Orgo bond assignment. So I've seen this come up like almost every semester. So deciphering between anti and gauche, all right, and comparing the two, they're both staggered, right? So Eric was saying that they're both staggered, but we're trying to decipher between the two, all right, because both are staggered, all right. So the difference between anti and gauche is, again, like Ashley said, anti is the largest groups. So not necessarily it's sometimes not necessarily the atom, but it's the group. So carbon, although carbon is smaller than a nitrogen, if it's a methyl, it takes up more space, right? So when we're talking about stability in a Newman, it's all about the something that that takes up more space. All right, that's often why we want terbutyl. It takes up a hell of a ton of space. That's why we want it in the equatorial position. All right, so anyways, deciphering between anti and gauche. All right, 3 here is anti. All right, why? So our biggest group on the front, so here's our biggest group in front on our front carbon, right? And here's our biggest group in the back, right? They are 180 degrees away from each other. So this is, again, our full circle. And if anybody didn't know before, all right, each of these is 60 degrees. All right, because again, we're referencing a full circle. All right, this is 60 degrees. So he could ask you, he could give you a Newman. It could be like, what's the conformation if I rotate the front carbon 60 degrees? Or 120, right? So you're gonna have to know. All right, so this is each little tick is 60 degrees. All right, the difference between anti and gauche, although they are both staggered, it's the difference in stability in that the front biggest group and the back biggest group are a full 180 degrees away from each other. All right, they are the furthest that they can get. All right. Now the difference between the thing with not anti, we just did anti. The thing with gauche is that, remember, if you didn't, it's like if anybody's French in here, correct me if I'm wrong, but it means like next to. So your front biggest group and your back biggest group are only one rotation away from becoming fully eclipsed. Right? Can you see that? So if I were to rotate this front carbon, just 60 degrees, it'll be eclipsing the back biggest group. You guys see that? That's what gauche is. That's the difference between, although they are both staggered, that's the difference between a gauche and anti. All right. So 1 is really the same thing as 4. So again, this front biggest group, this is all it would need to do is rotate it once. All right, this front biggest group and the back biggest group, although they are both staggered, it's not anti, because all that would have to do is rotate 160 degrees in order to eclipse the back biggest group. All right, that's all. All right. He would tell us in which direction to rotate it in, right? So he's not necessarily, So he could say clockwise or counterclockwise, in which that would be better. But he's more likely to give you a set of Newmans and be like, what's the conformation of this? Right? Or he could give you a bond line and be like, what conformation, if it was in a Newman, what conformation would it be in? In which you guys know how to, do you guys need me to go over how to go from bond line to a Newman? All right, that was a quick yes. All right. So I have a rule of thumb, all right? We know that the things here in green, I guess I'll put here in green, are on the plane, right? Does anybody not know that? In a Newman, right, if it's vertically up from the front or back carbon or vertically down from the front or back carbon, it's on the plane, right? It's not coming in or out. So would it have a wedge or dash? No. It's the things on the left and the right that are 3D, right? So if you're given a bond line, looking at the bond line, all right, and again, it sort of depends on the direction that he is telling you. All right, so these two carbons here are sp3, right? Something's going to be wedged and something's going to be dashed. Let's just make this the CO. And let's do this. Let's just make it a OH. Because no one likes just a boring butane. All right, so what this depends on, this always works, it just depends on the way you're looking at it. All right, if I were to look this way, all right, what's dashed is on the left. It's on the left here. There's dashed. If it was on a wedge, it's on the right. All right, so given this rule of thumb, we should be able to go from this bond line to a Newman. All right, so from this carbon here, I'll just say carbon 1. Carbon 1 has a methyl, right? Is that coming up or down from that carbon 1? Yeah, actually says down. So front carbon, that methyl is coming down. All right, so again, given this rule of thumb, we have a wedge and dash. Is the hydrogen going to be on the left or the right? Left. Now the chlorine, where is that going to be? On the right. Now instead of, let's just make that R. The right. All right. Back carbon, here I'll do in blue, so back carbon here. All right, it has a methyl coming off of it, right? Is that methyl coming off of that second carbon from this way of looking, up or down? So looking this way, this methyl, yeah, it's up. All right, now we have a wedge and dash, right? So where's the H going to be pointing? Actually says left. Anybody else agree or disagree? Where's this H going to be pointing on the Newman? Yeah, left. And where is that OH going to be? Really the only place, right? All right, so visually, let me try to do some fucking theatrics. All right, that should make sense, right? Don't mind me, this is not my closet. All right, I'm at somebody else's house. All right, so All right, so yeah. All right, so here I'm the bond line, right? So I'm so I'm the bond line. So something is coming into you. So if you're looking at a piece of paper and I'm on it, right? I'm the bond line. I have a chlorine here, right? It's coming, it's wedged if it's coming into you, right? And here, I'll do it with a fist, is my hydrogen, right? If I were to just turn to get to a Newman, right? We see how that rule of thumb works, right? This chlorine is over here, this hydrogen's over here. So that's the reason why this rule of thumb is what it is. All right. That takes care of having to do the mental gymnastics. All right. So if you're looking from the left, all right, so say, let me get rid of these numbers. Let's just let's number it correctly. 2, 3, 4. All right, so he's going to tell you what bond to look down. All right, he's going to tell you what bond to look down with your mind's eye. All right, if he's telling you to look from carbon 2 to 3, all right, he's going to put it in order at the direction he wants you to look at. All right, if he says C2-C3, he wants you to look down from C2 to C3. All right, and you'd be able to apply this rule of thumb in order to go from that bond line to the Newman for that given bond line. All right. So can I say that again? All right. So yeah, this rule of thumb here, purple, all right, is going from a bond line to a Newman. So he's going to tell you the carbon bond that he wants to he wants you to look down. If he tells you to, so given this molecule, I just numbered them. He tells you to, I want you to do the Newman for the bond of carbon 2 and 3, in which you would say C2-C3. All right. You use this rule of thumb I just circled in purple in order to get to that Newman. All right. The rule of thumb would not remain the same, Jamara, for the reverse, which makes sense, right? Because that, if you're looking from the opposite direction, that this OH really is, if you're looking at it from this way, this OH, what's wedged, is on your left. You see that? All right, so this rule of thumb works, all right? And most of the time, almost, I've never seen him ask the reverse, okay? I've always used this, but Lepore is sometimes getting real deep into stuff because he's our experimentalist out of all of us. But in general, this is the rule of thumb you can use going from your bond line to a Newman, all right? And so all he would have to do is say, hey, what is the Newman conformation for this bond line structure? So what would you do? Go to your Newman from the bond line, and there you have your conformation for that given bond line, right? Does that make sense? Any question, comments, concerns on this? And so with this same rule, you would be able to go from the Newman back to the bond line, right? Because everything is still the same, right? Because what you did to go to your Newman, you just do the reverse to go back to your bond line, right? So is there any question, comments, concerns on this conversion? All right, so has he ever, I believe Chris touched on it a little bit. in his former SIs from former semesters, but has he mentioned at all to you guys this semester about naming like carboxylic acids and esters and stuff and amides? Well, it's in the book, so I might as well. Nobody's gonna, I will, right? So let me just create a new page. I'll just do it right here. All right, so UPAC, we have our prefixes and suffixes, right? If you have a carboxylic acid, in which all of you know what they look like, right? Because this is going to come back, all right? And it sure as hell will come back in Orgo too, all these functional groups. All right, this is our carboxylic acid, right? If you were to be given this on a molecule, all right, nowhere can the carboxylic acid exist except on the end of a chain, right? Because you can't, if you have the chain continue on, then it's no longer a carboxylic acid, right? So this carbon here will always be your first carbon. All right, and the same with aldehydes. All right, again, this in red on a chain is always your first carbon. All right, not your last, even though it's on an end, it is your first. All right, and the suffix we use for carboxylic acid is oic acid. It's the only one that ends in the word acid. All right, and this ends in AL, not OL, but AL. All right. Similarly, but not similarly, but a little bit different, we have ketones, right? Ketones end in, can somebody take a guess? Own. All right. And the thing with ketones is that it's simply you just always want it closest to the first carbon. All right. So say you have this, for example. All right. Would you start numbering from the left or from the right? From the right. Right. So 1, 2, 3, 4, 5. So what would we name it? 2-pentanone. All right. It's just like how we usually do our IUPAC, but with that suffix at the end. Let's see if I can just type that 2-pentanone. All right. That suffix is telling us that there is a ketone on your second carbon, just as if it was a 2-pentanol. All right. That suffix tells us that that suffix, that thing that makes that suffix, is on your second carbon. All right. So that's your rule for ketones. All right. Just like everything else, we want it closest to the first carbon. You didn't miss it. I was just wanting to touch on some of this stuff because I've seen it on the test before, maybe once or twice, but I have seen it on Chris's SI handouts from previous semesters. Don't know why they're changing a lot of things, but it is what it is. So again, you always want your ketone on the thing that's closest to the first carbon. So if you were to be given this, right, a double bond, a ketone, your ketone wins. All right, if your ketone wins, would we start numbering from the bottom or from the left? So with this, if your ketone wins, yeah, from your left. So it'd be 1, 2, 3, 4. All right. There's 4 carbons in this molecule, right? So it's a bute, but it's not a butane. What is it? Yeah.
Butene.
Yeah, James. James made sure to remember that double bond, all right? Because we're indicating where everything is, right? So you have a double bond where on the molecule? At what carbon? 3, right? 3 butene, all right? What else is there? 2 own. All right, so it's just a matter of piecing that together. All right, so that's really probably the only thing that he may touch on is having a carboxylic acid or a ketone. Wouldn't we count from the right because the alkene takes priority? It doesn't. That's why. The carbonyls will take priority. All right. If you're comparing a double bond with a halide, not necessarily. If you're comparing an alkyl group, like in methyl, and ethyl, a tert-butyl, compared to, say, a halide like a chlorine, fluorine, bromine, your alkyl group will take priority. So let's see. All right. So here, all right, let's number it. All right, let's start numbering from the right. Based on what I just said, I just gave it away. Something takes priority. Yeah, from the right. Why? Because that takes priority. Not the ethyl, but the methyl. All right, so you guys are mistaking the longest chain. The longest chain starts here. All right, so if we're starting the lower substituents, yeah. So you start down here because this methyl takes priority over the halogens. All right, so 1, 2, 3, 4, 5, 6, 7, 8. All right, so I like to break things down and just piece it together. All right, so we have an octane. What else? We have a 3-methyl. We have a 4-bromo. And a 6-chloro. I don't even know if I spelled that right. So feel free to type it in the chat. What would the name of this be? Good, I actually got it. Methyl octane. All right. 4-bromo, 6-chloro, 3-methyl. Why in that order? Alphabetical order. That's all. All right. Now, there is a little caveat with that alphabetical order. There are things that we ignore when it comes to alphabetical order. Does anybody know?
Would it be like they're saying the die or like the ISO if it's like not one word?
Yep, so this is a perfect example. So this one looks daunting, but again, simply just break it down. Let me try to text wrap this thing. All right, so the longest chain, just so you guys don't waste time trying to do it. Yep, actually says 10, so we have a decane. All right, and again, like somebody else said in the chat, we want the substituents on the lowest number possible. All right, so if you start from the top or if you start from the bottom, if you add up those numbers that you get, which one gives us the lowest? Bottom or the top? The bottom. All right, so 1, 2, 3, 4, 5, 6. Oh, I feel my voice going. 7, 8, 9, and 10. So I like to break things down, me personally. All right, so we have a decane, right? We have a methyl on 2 and 3. So we have a methyl on 2 and 3. So it's dimethyl. Right. We have an ethyl on our 5th, so 5-ethyl. And we have, what's that thing on the 7th? Two. Yeah, isopropyl. Now you piece them together, and again, alphabetical order, but we ignore something. All right, so we ignore the things like di, tri, etc., and sec and terp. All right, sec and terp are simply short for secondary and tertiary. All right. So with this in mind, someone's jumping again. All right, and me personally, I have no shame. I still say the alphabet in my head. Let me see if she's right. A, B, C, D, E, F, G. B, C, D, E, F, G, H, I. Yeah, I becomes before M. All right, yeah, you guys are right in the chat. All right.
Still there.
Shh, I have my. God. All right. So, you guys good? If you're given multiple substituents, you put them in alphabetical order, and you simply just ignore those, just those prefixes. All right. Now, does anybody need me to touch on going from a name to a bicyclo, or the reverse? Either or, I can do. Anybody, doesn't matter if it's one person. All right, let's do it. Let me get a sip of wine. It's a margarita for people that want to know. Let me know in the chat what your favorite drink is. All right. So water. Man, you guys are weak. Bleach. Tide Pod. Yeah, remember that? Tide Pod. I'm hoping, I have faith in you guys that none of you did that Tide Pod challenge. Monster. Yeah, it's all right. Sprite, just if you want to know, I have a recipe. 1 part, what do I make it with? 1 part vodka. All right, 1 part vodka for the person that said Sprite, Valentina. All right, 1 part vodka, 2 to 3 parts Sprite with a splash of whatever mix you want. I'm telling you, it's good. All right, McDonald's Sprite. That'll wear the enamel off your teeth. All right. Bicyclo 3,1,1 heptane. All right, so some of you, most of you, I would say, are in one of my sections because I did post this to some group chats just in case. Last semester, I actually had somebody from like freaking California that joined my thing. All right, so Madison, those of you that know Madison, she's awesome at what she does. She's great. We just have a different method. All right. I personally start with the chair. I mean, not shit. I personally start with the bridge. All right. So with this one here, all right, is there a carbon on the bridge? And if so, how many? 1.
1.
What's up, Yuri? So there, that's what we look like, right? Here's our bridge heads in red. Here's our bridge heads in red, and there's our 1 carbon on the bridge, right? I like to do it this way. I like to start this way because then you just fill in the left and the right side. You don't have to try to figure out, the other way around, which is what Madison does. I like to start with the bridge because a bridge, it's almost like you're driving over it. You have your left side and you have your right side. You're looking to the left side of the water and the right. All right, so once you get your bridge, just fill in the rest, right? How many carbons is on our longest side? 3, right? So let's just go to the left. There's a first, second, third. And how many is on the other side? And i.e. the shortest side in this case? 1. And you're done. Does it matter which side we choose for the 3 C's? No, because if you do the right side, you're just going to end up with the mirror image. So if you do your 3 carbons on your right side, you're just going to end up with a mirror image. It's the same exact molecule. All right. And that, I just realized, looks like cat eyes. All right. So yeah, that's how I personally do it. All right. So again, start with the bridge. That's how I do it. That's how I recommend it. Start with the bridge and then fill in the gaps. All right. So let's do this one because this does have a carbon on the bridge and a substituent. All right. How many carbons are on this bridge itself? The bridge itself, it's that last number, 1. That's what our last number tells us. That's why I preach looking at the bracket. So that bracket will tell you a hell of a lot about your bicycle. All right. So how many is on a left or the right side? Start with 1, 2. All right. And the other, yep, 2. All right. So just so you guys know, this is a base structure that you guys are going to need to know. All right. So if you want to practice a chair or if you want to practice a bicyclo, just draw this over and over. All right. So this one also tests your numbering. All right. Where do we start numbering? What's the thing called that we start numbering at? Bridgehead. All right. So let's ambiguously pick this one. All right. So if that's number 1, all right. Is there any longer side to this molecule that we need to consider? Or can we go to either side?
They're all the same.
Why was it for the bicyclos? Why is there only like 1 carbon on the bridge? Wouldn't it be 2 since it's the 2 in the middle?
No, it's the third number. So the third number tells us how many carbons are on the bridge.
Okay, so why is the chlorobicycloheptane the same, or not the same, but it has a similar bridge as the first one?
So this is from me answering somebody else's question. This is the mirror image of that.
Oh, okay.
Yeah. So she asked, so starting at the bridge, if it matters which way you fill in, left or the right, I said no, because you're just going to, going to the opposite side is just going to end up with a mirror image.
Okay.
Yeah. So this is just the mirror image of that. So you guys said no to the other question where you don't have a preference for going left and right. All right. So let me just go to the right. So that's 1, 2, 3, 4, 5, 6, and another pattern if you guys want to know it. Your last numbered carbon is always the one on the bridge itself. 7. Now there's something else on this molecule. What is it and where? There's something missing with methyl on the 7. Boom. That's the molecule. Now you're done. All right. So if the last number in the molecule, if the last number in the bracket says the number of carbons on the bridge, what does the number 0 mean? There is a bridge, but there's no carbons on the bridge. All right, so yeah, Jake, it's fused. All right, so you have a bridge head, you have bridge heads. All right, so you have a start and finish to the bridge. You just don't have a bridge. You just don't have a carbon on the bridge itself. So it's flat. All right. So it's like those bridges that come way up high. You have to drive way over them versus the ones that just run along parallel to the water. All right. Now you just do the same thing as you did before. You have a longest side, right? So the longest side has how many carbons? 3. And the other side has how many? 2. All right. And like usual, we start counting from the bridgehead to our longest side. All right. So where do we go, left or right? Left. 2, 3, 4, 5, 6, 7. All right. And here we say that there's a chlorine on the second. So you just place it where it's numbered number 2. All right. So again, there is no triangle on the bridge. All right. But again, this is in 2D. All right. If I wanted to make this thing on the left in 3D, this is 3D. If I wanted to make it in 2D, it would look like this. All right. It's the same exact molecule. All right. It's just flattened. It's just looking at it from above down, 2D. All right. There's no difference between the two. It's just a vantage point. Doesn't matter here. We numbered it to the right. We didn't. So which one? The middle one, we didn't start counting to the right. So if you look here, here's 1, here's carbon 2, Here's carbon 3, here's carbon 4. But to answer your question, it does matter because you're counting, you go towards the longest side for bicycles. All right. And Eric, yeah, so that's the pattern that I want you to recognize. If there is a bracket and there's 3 numbers in the bracket, it's a bicyclo. All right, because it indicates that there is a bridge of some sort. All right. Now you guys have been sent out by Roche a handout or practice problems to go over. You guys saw Spiro in that, right? Is anybody confused on Spiro? Lepore, you know, knowing him, he probably touched on this in lecture, but you guys maybe didn't go over it much. Does anybody need me to go over Spiro? All right, Spiro, all right. Yeah, all I know is it looks like a bow tie. It's because it twists on itself. It almost looks exactly like a twist boat, right? Yes, Jamar, it has no bridge. So it does not even have 3 numbers in the bracket. So our 3rd number in our bracket typically tells us that there is a bridge and how many carbons are on the bridge, right? If there is no bridge, then there is no 3rd number, right? So if you have a spiral molecule, Spiro is what it starts with, you only have 2 numbers in the bracket. All right, you only have 2 numbers in the bracket. Actually, let me correct that. You only have 2 numbers in the bracket. Now, I mentioned this to those that are my students. I mentioned this before. Does anybody know why I put the smaller number at first? All right, so the reason why I did that is because when you're given a spiral molecule, you start counting, you number the smallest side first. All right, Eric, I remember your name. You are a student of mine. You do know that spirals exist. You just didn't pay attention. All right, so the twist itself is carbon 1. All right, the twist itself is carbon 1. All right, Spiro, not bicyclo. All right, Spiro is the only case in which you start counting to the smallest side. All right, so would we go left or right? Left. So this is 1, 2, 3, 4. We already counted that. 5, 6, 7, 8. All right, so you get Spiro bracket total number of carbons. All right, that's all you need to know for Spiro.
I had a question.
Yeah.
Why you didn't start the long way again?
It's just convention for spiral molecules.
So it's
It's just the rule. There is no logic really to it. It's just the IUPAC naming convention. So bicyclos, i.e. if there's 3 numbers in the bracket, it's a bicyclo molecule. You start counting to the longer side. If it's a spiral molecule, 2 numbers in the bracket, you start counting to the smaller side. Cool? And yeah, I just didn't number it. 9. All right. That's all you need to know for spiral molecules. All right. Cool.
What does the 2 and 3 represent? Because I don't see what it correlates to.
2 and 3. Yeah, I made that up before I even drew a molecule. So the correct numbers would be what? How many carbons are on one side and how many carbons are on the other? Yeah, we got 3 in the bracket, and we have 5. All right, we have 1, 2, 3 on one side, and we have 1, 2, 3, 4, 5. All right, so in the bracket, it would be 3 and 5.
Okay.
Cool.
Yeah. For the bicyclos, what I understand, like the last number is supposed to be the amount on the bridge. What
Yeah.
are the other numbers?
What if there's more than one more than one?
No. I mean, like for for regular bicyclos, not the spiros. What do the 3 numbers represent? Because I know the last one is the amount on the bridge.
All right, so the first number in the bracket, so in the bracket itself, the last number, again, tells you a lot. If there's 3 numbers at the bicyclo, and the last number, like Eric said, is the number of carbons on the bridge itself. So if it's 0, there is none, it's just fused. And if there is 1 or up, that's how many's on the bridge. The first number tells you the longest side. That's the association with that, is the longest side. The second number, if applicable, is the smaller side. So the perfect example of that is this one here in the middle. All right, you have 3. All right, 3 indicates your longest side. So you have 3 carbons on one side, and you have the middle number says 2. So you have your second number on the smaller, which is just so happens to be the smaller side, on the other side of the bridge. All right, so yeah, that's that. Now you should be able to, there should be more here. All right.
He's frozen.
Is it frozen for you guys too?
Yeah, it's frozen.
Oh.
You guys good? Everybody here still? My computer died.
Yeah.
All right. I'm doing this from the floor. So you should be able to do this again, given a structure. All right. So again, so this molecule tells you the numbers in the bridge, right? What do our numbers in the bridge mean, and how can we do that? Yeah, you guys I didn't share. All right, here we go. All right, so given this molecule, we should be able to figure out the name of it, right? So given this molecule, let's start with the bridge, because that's how I like to start. All right, let's start with the bridge. So the bridge is what? All right. There's 1 on the bridge. Yep. So there's 1 on the bridge, and it is a bicyclo. So there's 3 numbers in the bracket. So we have 1 as our last number. All right. Now how many is on each side of the bridge? So does anybody disagree with Ashley? Does everybody understand that? Because, yeah, that's right. So it would be 3, 3, 1. All right, that's our bracket. So bicyclo 3, 3, 1. All right. And our parent is just the total number of carbons. All right, so in starting our numbering, let's start. Is it number 1 on top or is number 1 on the bottom? So Ashley says top. Yeah. Yeah. All right. Yeah, it's on top. Why? Because it's the closest to the substituent. And again, we want our substituents on the lowest number possible, so we start counting in which direction? To the right. 2, 3, 4, 5, 6, 7, 8, 9. All right. So you have a bromine on the second, right? So 2 bromo. Bicycle, because it's a bicycle molecule. Bracket. We figure out the bracket. And what's our prefix for 9 carbons? All right.
Does it matter if you put the dashes between the labels?
What labels?
Like the name, so like 2 bromo dash bicyclo 331 dash no name. Does it matter or it doesn't?
It doesn't really, because there's not really anything. You're not really saying anything else. You're not saying that there is something else there and where. So if there's a dash there, it's no different than doing that. Right? It's kind of like methyl pentane. Would you put a dash between methyl and pentane? Right? It's no different than that. So you guys good for drawing bicyclos or going from a bicyclo to the name? Any question, comments, concern? All right, so chairs. Somebody mentioned chairs. Does anybody want me to touch on chairs? Yeah, that's a quick yes. All right. So he could vary. This is a perfect test question. He could ask you, he could give you a name and be like, what conformation of it is more stable? Or he could give you a name and be like, what's the structure, right? So given that he's asking you for a chair, I personally like to start 2D. If he gives you a name and he asks you for a chair, just do 2D first, all right? 2D, meaning not a chair. 2D, draw it flat. So what's our parent chain? Cyclohex. All right, and we have a tert-butyl and a methyl on the first carbon. All right. Now these carbons are sp3, right? Yes. No. Would be yes. All right. So the tert and the methyl, one of them is going to be wedged, one of them is going to be dashed. So just for the sakes of ambiguity, I don't know if that's the right word, but let's just draw the methyl. And let's just draw this tert-butyl. All right. So this, I'm saying, is our first carbon. All right. Now you go to the chair. All right. Because now you have some sense of direction where the substituent should be pointing. Right. That's bad.
Sorry, how did you decide what's wedged and what's dashed again?
So it could be either or. So the name doesn't tell you which is what. if the name was telling you that, it would tell you an R or an S of it. All right, that's the only way that you could know which is what. It's just asking you, given this name, which one of these conformations is more stable. So you could just test yourself with both. But there's a rule of thumb that I like to use. Does anybody know it, to figuring out the direction? All right, if something is wedged in 2D on the chair, yeah, you guys are good. Wedges up, dashes down. All right, so let's just say that this is the first carbon. All right, if wedges up, dashes down, all right, that's how we draw it. All right, wedges up, what is up? Tert butyl or methyl?
Methyl.
Methyl. All right, and tert butyl is, all right. So now you're able to call something axial or equatorial. How do we figure that out? I'm sure somebody here memorized that diagram in the book.
The axial straight up.
Okay, so the axial position is straight up, and on another carbon it could be straight down. So if you want to recognize a pattern, if something is vertically up or vertically down, just vertical, it is axial, right? Equatorial, it's going to be on a diagonal, right? It could be diagonal up, it could be diagonal down, it could be diagonal to the left or right. If it's diagonal, if then it is equatorial. All right.
I had a question.
Yeah.
Somebody was talking.
Yeah, just real quick. So the terabutyl is the biggest looking, or the biggest thing there, just because there's so much on it. Like, so that being equatorial makes it the most stable. So the biggest group has to be equatorial, right?
Correct.
Okay, cool.
So it can exist in an axial position, but how would we get there? If I wanted to make this axial, if I wanted to make this terbutyl axial and this methyl equatorial, what would I do? What do we call it? Yeah, a chair flip. Right. But yeah, you are right, Eric, that the preferred conformation with regard to stability will always be the thing that takes up more space to be in the equatorial position. All right, go ahead, Gary.
And he asked the same question I was asking. I was going to say, would it be the same case if it was like an ethyl compared to a terbutyl?
Yeah, an ethyl takes up more space than a methyl. Right.
I have a question. Do you go by Mike or Michael? Do you have a preference?
Nope.
Okay. All right, I'll call you Mike then. If we're doing a chair flip, I know this is not directly pertaining to what you're doing right there, but if we're doing a chair flip, can we just move the position over one in order if we were trying to see how something would change for the flip, or do we actually have to manipulate the structure?
So the structure itself is going to change upon a chair flip.
Yeah, no, I know that, but I remember Chris doing in one of his SI sessions, I just can't remember it now, and we can't access any of the videos. I think he did one where he just moved it over one position.
So if you left, so again, this is ambiguous. So you could just say, so going from the top to bottom here, we did not do a chair flip. All right, so you couldn't say that this is your chair flip. You couldn't say that. All right, because this is that first carbon. So this is carbon number 1. All right, you do have to do a chair flip. What he meant by rotating positions.
No, he moved like that number, that 1 went back 1 position. It didn't stay 1. That's what I meant by that. He moved.
So I know what you're getting at, and that happens because you do a chair flip. So So you do your chair flip. So this comes up, this carbon comes down. All right. So this, because that carbon came down, this is now carbon number 1. All right. Don't they both have to go in the same direction too? So yeah, if as you guys practice chair flips, you guys will notice that if something was pointing down in one and you do a chair flip, it will still be pointing down in the other. That does not mean it stays axial or equatorial. That does change. The position where it's pointing on the paper doesn't. So that equatorial, that methyl will still be pointing up, and that terbutyl will still be pointing down. But the equatorial and axial change. All right, and now, does anybody know my trick to figure out where an axial position is? Mentioned it a few times. It's an elbow. All right, the points. Yeah. So let's just look at that one. All right. So that I like to call that an elbow. So elbow up or elbow down. Is that elbow pointing up or down? Up. So axial is vertically up from that position. And this works for any of them. All right. This carbon just happens to be carbon number 1 that we labeled. That elbow is pointing where? Up or down? Down. So axial from that carbon is vertically down. Cool. All right. And if axial is vertically down, then equatorial is diagonally up. All right.
Michael, I have a quick question.
Yeah.
So if equatorial, or if, in this case, terbutyl is the most is equatorial to make it the most stable, how do we know that like this, or having it on the tip of that, is the most stable? Why wouldn't we just put it anywhere, I guess?
So yeah, I know what you're saying. So why that carbon in particular? Again, I just picked it because we are used to seeing things on that carbon. So you could just call that carbon number 1, right? You would still use that rule of thumb, wedges up, dashes down. So so if we wanted to call that carbon that I have on an arrow, if I wanted to call this carbon number 1, all right. Now wedges up, dashes down, right? Mm-hmm. Terbutyl's down from that carbon. From that carbon down just so happens to be what position?
Axial, but I'm more talking about like on the top part, like, because if it's on the top part, then the terbutyl will point up.
Okay, so you're saying if this top one, if the terbutyl was here?
No, I'm talking about like, do you the carbons on top of one, like to the left of the original one you made. Like the first conformation you made to make the most stable, if you were to have one go 2 carbons to the left.
So if you were to have carbon number 1 be this one?
Yeah. Why wouldn't we put it there if it's... Would that make it equatorial or no?
All right, so say we have that as carbon number 1. Let's just see. Okay. So if that's carbon number 1, all right, methyl is going to be pointing up in some way, shape, or form. We don't know if it's going to be axial or equatorial. And the terbutyl is going to be down in some way, shape, or form. All right, so from this carbon, pointing up is the methyl, right? And now we can say, is that axial or equatorial?
Axial.
Axial. And now downwards from this carbon is our terbutyl. And now we can say if that's axial or equatorial, and which is it?
That's equatorial.
Equatorial.
So why wouldn't that conformation be the most stable instead of the other one, like the original?
So when you're comparing most stable, you're often comparing axial and equatorial. So if you were to do a chair flip from that, let's do a chair flip. So this, okay, to answer your question directly, this isn't any more or less stable than the previous one.
Oh, okay.
Because at the end of the day, you're in a chair and you have your biggest group on your equatorial position. What do you mean by when you say up, down, stays? But so, all right, so this will answer your question. All right, so this comes up, this comes down. All right, so let me just number. So if that was 1, 2, 3, 4, 5, so this would be 6. So this is 6. That means this is carbon number 1 now. All right. Now, this terbutyl becomes axial, right, upon a chair flip. If it started in an equatorial, which it did, it becomes axial, right? Now, carbon number 1, which way is that elbow pointing? Up or down? This elbow of carbon number 1, is that pointing up or down?
Would it be down?
Down. So axial is vertically down. That means equatorial must be diagonally up. There's your chair flip between these two. All right, so to answer the question in the chat, do you see now that it's not something that you have to remember, or it's not really a concept. It just so happens to be that this started pointing down and it stayed pointing down. But the configuration changed in which it changed from equatorial to axial. That answer your question, Jamera? Can it be axial up and equatorial up on the same carbon? No, it can't. So axial and equatorial are always pointing in a different direction when you're looking at the same carbon. So again, this position on this carbon is axial. How do we know that? Because the elbow is pointing down. And this would be its equatorial position for that carbon. All right.
I had a question.
So you cannot have that. Yeah, go for it.
Is this molecule considered a trans? Because it's one's axial is one's equatorial.
Yeah, so not even that, but look at this, right? So this N2D, your two substituents, right? Your two substituents, are they pointing in the same direction? Are they both wedged or are they both dashed?
No.
No. Right. So yeah, we can do chapter 6. Right. All right, so I will, here, since we are moving from chapter 4 to chapter 6. Here is this handout. So again, there's these textbook problems. There's bonding examples and a former quiz question. All right. And here's my answers in solution for that handout. All right. So in the chat, I just posted both things for chapter 4. Right. Let me see if I can do more for you guys. So there's everything you need to know for chapter 4 in the chat. So moving along to chapter 6. Do you guys see the files that I put in the chat?
Is it Organic Chemistry Chapter 4 docs?
Yep, that's one. And there's week 4 handout answers and week 4.
Okay, thank you.
Yep. So week 6, chapter 6. All right. Let me ask you, what's a leaving group?
The chemical that leaves during the reaction.
Yeah. So hopefully that's in the name. Right. Hopefully somebody did not just question themselves when I asked that. All right. So here's the first page of this is chapter 6 summarized. All right. So you have your substrates. All right. The major difference between SN1 and SN2 is the fact that SN1 has an intermediate which cares about stability. All right. There is a slight difference between nucleophile and base. They're very similar. It's just a verbiage almost kind of thing. Leaving groups is again literally what leaves the substrate. And if you've seen OTS before, but haven't seen the structure, that's the structure. All right. If you see that structure, that for sure as hell is leaving that substrate. All right. And there is a trend for leaving groups. All right. Bigger the better, and more electronegative the better. All right. Which makes sense, right? If I'm on a cliff, right, and I'm trying to hold a buddy from falling off to the bottom, right? Am I more likely to let go of a buddy that's 250 pounds, or am I more likely to let go of somebody that's 100 pounds? The bigger dude, right? So again, the bigger things leave the substrate, all right? But if you look at this trend, if they are in the same group on the periodic table, so these are the main ones, there are usually halides, all right? So this is carbon, nitrogen, oxygen, fluorine, then chlorine, then bromine, then, all right. So despite fluorine being more electronegative, that size wins, all right. So this is not asking you acidity. We know about acidity. This is asking you just the relative speed at which something leaves the substrate, all right? So the general trend would be like that. Cool. All right. So polar protic, polar aprotic. A lot of people a lot of people confuse this. If you're non-polar, you're non-polar. All right. Just carbons with hydrogens or something that's not electronegative in hydrogens. All right. Which should just so often be hydrocarbons. All right. If you're polar aprotic, you're polar, right? Obviously. And you don't have hydrogen bonding. All right. A lot of people overthink giving and taking a hydrogen to determine whether it's polar or aprotic. Hydrogen bonding. All right. If it has hydrogen bonding and it's polar, then it's polar protic. Cool. All right. Reaction rates. Reaction rates have nothing to do. You don't have to look at the products at all. All right. You don't even have to look at the solvent. All right. You simply determine the type of reaction, SN1 or SN2, and that will tell you how to do the reaction rate. All right, here's the reaction rates. All right, SN1 is only dependent on the leaving group, or i.e. the substrate where the leaving group came from. All right, so if you double the concentration of the substrate, what happens to the rate? Doubles, right? If I double the concentration of the nucleophile and the substrate, what happens if it's an SN1? Yep, it still only doubles because it's only the substrate that affects SN1, right? If you double either of them, all right, or if you change the concentration of either of them, it could be increase or decrease of either the nucleophile or the substrate, and it's an SN2, then the reaction rate will be affected. All right. Cool. That's really as much as you need to know. All right. And this here I will put in the chat because you guys can use it when answering questions. All right, so this key is the key to determining the type of reaction. All right, that's what you need to know. All right, somebody in here joined my office hours on Wednesday. They already got a head start. They already know this chart. All right, this chart is your go-to, is your godsend for determining the type of reaction. All right. So if you have a tertiary substrate, it's going to be an SN1 reaction, right? If you have a primary substrate, it's going to be an SN2 reaction. Cool. If you fall in the middle on secondary, then you look at the strength of the nucleophile. If it's strong, then it's SN2. If it's weak, then it's SN1. And what's a rule of thumb that you can use for determining if it's strong or weak? If it's negatively charged or not, right? Because what's a nucleophile? The nucleophile is the thing that's using its electrons to go get something or go attack something, right? If it has more electrons, then it's more negatively charged, right? So it's a stronger nucleophile. Cool. And the last thing you probably need to consider is the solvent, right? In which I just went over how to determine the solvent. Cool.
You broke when you said that about the solvent. I don't know if it did for anybody else. You said that the solvent, I heard barely any of it. It's okay, I see it up there. Thanks.
Yeah, so if don't overthink it, all right? A lot of people try to overthink it, whether it's going to give or take a proton or whatever. I don't even know what people think. I mean, I was in your shoes, so yes, I get it. To make it all simple, like I've been trying to do since we started, is if it's polar and it has hydrogen bonding, then it's polar protic. Cool.
Yeah, thank you.
And again, for everybody, I already put this in the chat. It's called week 6. All right. So here, I mean, I already have circled the answers, but I'm just going to ask you why. All right. Via an SN2 reaction, why is the one on the left, the top left problem, why is the one on the left more rapid?
Because there's less blockage.
So people in the chat are saying primary. That's all you need to know. All right. So again, look at that chart I put in the chat, week 6. That chart will tell you. All right. SN2 reactions happen faster and faster in a primary substrate, in which this one is. All right. Now, this one on here. All right. Let me ask you why. Why is the iodine faster? Why is the one on the right faster? You don't even have to consider the type of reaction, really. What did we say? This is a substrate, and so that chlorine's going to leave, that iodine's going to leave, because it's it's better leaving group. And yep, Eric, it's better leaving group because it's bigger, right? This one, although these are both primary, the one on the right here is going to leave because it just has less steric hindrance. There's not much, there's just less. All right, there's another example in which it doesn't occur at all, but I have down below. All right, this one on the bottom right, if you ever, in this course, all right, in this course, you'll see it a shit ton in Orgo 2. In this course, if you see a halide, if you see a leaving group directly attached to your benzene ring, it will not occur. Cool. You don't need to know why. You don't need to know the orbital reasons or anything like that. That's Orgo 2. All right, just know that that won't work.
Excuse me, Michael, is it any kind of ring?
So it'll work with, so it's mainly the benzene ring. If it's a ring with those pi bonds around it, then it's a benzene ring. And so if you have a leaving group directly attached to the benzene ring, then it will not occur. And no, it does not. It's regardless of whether it's SN1 or SN2.
Okay, so no double bond rings. Got it.
Correct.
What about if it had like but it would be a primary though, if it had like a CH2 in between it, would that be okay?
Yeah.
Okay.
Yeah. So yeah, that's an obvious reason why this one is going to work. All right, so this one, again, it's just everything's the same. So even looking at this one being said, regardless of whether it's SN1 or SN2, which one of these is going to occur, 1 and number 2?
One.
Yeah. It only brings up number 2 because technically it sometimes occurs, and you'll learn why in Orgo 2 for this class. It does not even, so can you explain why it's number 1? Because if a leaving group in this course, keyword, in this course, if you have a benzene ring with a leaving group directly attached to it, you will not have a substitution reaction. That's all you need to know. All right. That answer your question? The question below. Yeah, it's the same thing. So this question, so number 2 here, the leaving group is directly attached on the left. Okay, so yeah, we already did the one on the right. Let's do the one on the left. All right. So why is this one number 1? Does anybody have any idea? Everything is the same. The leaving group's the same. The substrate's the same. Does anybody know why? If the substrate's the same, the leaving group's the same, what's going on? And both solvents are neutral. Yes, water is better. All right. Okay, so amylase. So both are protic. So both are polar and both are protic. It's just a matter of which one's more polar. That's all. All right. And which water is more polar than methanol. That's all. All right. All right. So this is just a retro thing. So it's just asking you given, again, so a lot of people tend to overthink this when they're doing their end of chapter. So if you start with this, how do you get to these? All right. So all you'd have to do is just pick. It's just ambiguous. These questions, it's not really a right or wrong. You can really pick anything that would get you these. It's just these questions at the end of these questions at the end of the book are just purposely to make you practice. All right. All right. So here's some better ones. This. All right. You guys pull up that chart. I put it in the chat. Pull it up. All right. This substrate is what? What's the classification of that substrate?
Is a
Substrate. Actually, substrate has nothing to do with polar protic or aprotic.
Is secondary?
Yeah, secondary. Look at the leaving group. The leaving group's the Cl, right? Is that leaving group primary, secondary, or tertiary? More than one person to give me some hope. That leaving group is secondary. All right, so we have secondary. All right, and now, so given that it's secondary, we got to look at the nucleophile. Got to look at the nucleophile now. Is that strong or weak? What was that rule of thumb I said before? Is that strong or weak?
Strong.
It's strong. So secondary and strong gives you what type of reaction? Then just look at that chart.
SN2 reaction.
Yep. So you have your chair. Everything stays the same. It's just that Cl gets replaced with a I. But what's something else that we got to consider with SN2? Does anybody know?
Transition state.
Nope. SN2s do not even have a transition state.
Is it like it deals with like basically the chlorine and hydrogen.
Stereochemistry. What
Like
happens?
an inversion.
Inversion. So SN2s always invert their stereochemistry. All right, so if this was pointing up, then it must end up how? All right. Cool. So that's because that happens because it's an SN2 reaction. If it was SN1, you would get both. If it was SN1, hypothetically, it's not. But if hypothetically it was SN1, you would get both. Right. Cool. And what's it called? What's the products called? Like why? Like we have something. Yeah, I didn't know how to ask. It's racemic. All right. SN1 reactions produce a racemic mixture because you literally have a mix of both conformations. All right. So another example here, all right, is the substrate primary, secondary, or tertiary? Look at the leaving group.
Secondary.
secondary. So secondary, all right. Now, given that it's secondary, we got to look at the nucleophile, all right. Somebody give me something. Strong or weak? Why do you think so? Actually says weak.
Shouldn't it be no reaction because of the ring?
No, there'd be a reaction. The leaving group isn't directly attached to the ring. It is strong. All right. Remember chapter 3? All right. Like dissolves like. Remember how things dissociate? That sodium is going to dissociate. So your nucleophile really is this methoxide. See how it is actually strong? So again, if you're a student of mine, this is why I said get your chapter 3 shit right, so it's easier in chapter 6. So secondary and strong gives us what again?
SN2 reaction.
SN2. So everything is the same. We're just changing what? Only one thing changes. What is it?
The chlorine.
Yep, that chlorine gets replaced with that OCH3, not the position of where the Cl was, but the stereochemistry, right? If that chlorine started as a wedge, how is it going to end up? As a dash, because it's an SN2 reaction, keyword SN2. All right. If it was an SN1, you would have both it being on a wedge and a dash. Now, this is your example of a primary substrate and it not occurring. All right. So primary substrates, again, primary substrates prefer what type of reaction? Just to go through the rationale.
SN2.
Yeah, so again, let's chart primary substrates, SN2. Okay, what do we say that SN2s care about? They care about sterics. All right, so when that leaving group leaves, you have your carbocation. All right, but do you see how our electron cloud, right? These methyls each have their own electron cloud. All right, they're going to interfere with the space that this nucleophile can come in. All right. So think of it as, you know, you yourself are the nucleophile and you're trying to walk through a crowd or you're trying to walk through a single file line. If you have a lot of steric hindrance, you're trying to walk through a crowd, right? Is that going to work? No. You can walk through a single file line, right? You can't walk through all that hindrance. All right. That's why this does not occur. All right.
What was the name of that again? Was it pentane or not pentane? What was that called? Like that phenomenon of like no reaction because of the 4 carbons?
You mean neopentyl? That was what.
Oh yeah, that.
Yeah.
Yeah, that's just the functional group. Yeah. So if you want to think about it that way, say this was a parent chain, this would be a neopentyl. All right, and the reason why this does not occur, this reaction is no reaction because of the steric hindrance. All right. If it was 2, all right, if there was not 3 methyls, but it was just 2, it would occur. all right, because there would just be less steric hindrance. All right.
Is that in that case, it's still considered a primary carbon, the one that's attached to the alpha carbon?
Yeah, so the leaving group is still considered a primary leaving group, but
Okay.
doesn't occur because of the sterics.
No, I meant in the other case that you just gave, if it were 2 carbons, instead of it being this neopentyl here, if it was just the 2 carbons. Yeah, like that.
And if it was still primary?
Yeah, like I meant it would be primary in that case, right?
So it's still primary because how many carbons is this attached to?
Just the one.
Just one.
Okay. All right. Just wanted to make sure.
So this is, I mentioned it before in chapter, when did we classify alcohols and amines? Chapter 2. All right. So chapter 2, you classify your leaving group the same way you classify your alcohols. Same exact thing. All right. So, all right. So this one, primary, secondary, tertiary substrate. Someone says secondaries. Why? Because that's not it. It's not primary either. It's tertiary. All right. So again, this, how many carbons is that carbon attached to? 1, 2, 3. All right. If you're struggling on that, again, review how you classified alcohols. That's for any leaving group. Leaving groups is classified the same way as we classify alcohols. So that substrate is tertiary. So what kind of reaction is going to occur? SN1. All right. Because why? Because what do SN1 reactions care about? I said it before.
Is there any way that you can, with one of the SN1s, you can actually do the products for us?
Yeah, so this SN1. Right. So you get both. You get both conformations, right? So you're still, in one of your products, you're still going to have your methyl as a wedged. But the nucleophile is replacing that OH and going to be is a wedged, and your methyl is still a dash. All right. But because it's SN1, you get both conformations. Right, not an arrow, but you get both. All right. So your other option is this.
I don't know. I'm getting confused though. Where does so that dash has the not the dash. I'm sorry. I feel like after you see this, and especially at this time of night, you start like everything starts looking the same.
Mm-hmm.
The OH, where does like that actual whole OH leave and then the other one comes in? That's what I'm getting confused on what's actually like changing places here with this particular one, since this has an OH there and then there's an OH there.
So this is your leaving group, so that does leave. So curved arrow wise, it's going to look like this. So you have this floating around in solution, right? Now I'm assuming you're wondering, like, why isn't there an H here?
Yeah, like I just didn't know what was exactly happening, I guess.
Okay, so this, somebody said in the chat, deprotonation. All right, this will go ahead and remove this hydrogen from that.
Oh, okay. I remember now. Now I remember.
So in your middle step, this occurs. and now it's just no different as if now it's just no different as if you dissociated a metal. Now this comes in and attacks your alpha. All right, that Cordero is wrong. And Corderos are lone pairs.
Thank you.
No problem. All right. So this, I've seen this come up on a quiz before. Did you guys take your chapter 6 quiz? And if so, did you see this question?
I took chapter 6, but I don't remember seeing these.
Yeah, that was on our quiz. Is this the one where it flips back on itself?
Correct.
Yeah, this was on our quiz.
So good thing if you're a student of mine, you get formula quiz questions. All right. So, so this is called an intramolecular reaction. Is that cheese? Yeah. I like cheese, guys. I like cheese. Okay. All right, so lost my train of thought. All right, so again, the salt dissociates, right? And you're left with this. All right. Now let's run through this. What happens? What just happened in the previous that's going to happen in this one? Who was it? Lynette, Farah, is deprotonation. All right. So it wants to gain a hydrogen. Where is it going to gain that hydrogen from? Boom. All right. So intermediate is this. Cool. You good with the first step? Is anybody completely lost on that first step? No shame. All right. All right, so nothing else is going to react with this thing. All right, there's nothing else in solution that's going to react with this because this solvent is unreactive. All right, it's not going to do anything. This solvent is just this. It's not going to do anything. All right, so something's going to happen with this. All right, you have this oxygen species is going to act as the nucleophile. All right, so your BR, that's your leaving group. Your BR leaves. All right, again, I'm just breaking everything down right now. The BR leaves. All right, so you're left with your carbocation, your alpha carbon. All right, and if that oxygen is acting as your nucleophile, what's going to happen? The electrons on the nucleophile are going to go there. That's where you get it folding in on itself. All right, so what's our answer? All right, so every time there's an OH, it's going to be deprotonation. It's not necessarily true. The deprotonation has to do with the solvent as well, or if there's something else in solution that's going to deprotonate it. So like this example that we did before, all right, this was in solution and was able to deprotonate it. Deprotonate your salt in this case. All right, is there another example that I have? All right, so this, if you were to go from this to this, or even the reverse, right? Say I have this as a reactant. I'm going to that. Just because it's an alcohol, that does not necessarily mean there's a deprotonation occurring, all right? Because you can have a solvent that's not protic, right? You can have a solvent that doesn't have a hydrogen to deprotonate, right? So if there isn't a hydrogen to deprotonate off your solvent, then there isn't going to be a protonation that's going to occur. So this is just going to leave, and you have a Br somewhere. Let's just say NaBr. It's going to come along and replace it. All right. So that's not a rule of thumb that I would advise. All right. So every time there's an OH, that does not mean there's going to be a deprotonation. All right. So it all comes down to if deprotonation occurs, it's because there is something in solution that's going to deprotonate it, not just because it's an alcohol. All right. So yeah, does that clear that up? Does everybody understand how this occurred? I'm sure probably people got pissed seeing that on the quiz. But good thing if you're a student of mine, I posted this earlier this week.
So is this like, I'm not sure. So the H, so we have I'm just confused on the negative H2 that's in the top part of the arrow.
Don't worry about it.
Oh, okay. So we just say that the H, I'm not sure why the H interacts, or the hydrogen interacts with that hydrogen, and
it's no different than if it was Na, what? OH. It's no different than if it was NaOH, right? Because that Na would dissociate and you would get this.
Oh, the OH takes the hydrogen, becomes water. This is becoming whatever H2 is.
Correct. So this is, you don't really have to worry about this, all right? That's not telling you what it's going to become, all right? That Na dissolves away, so you're left with Na plus floating around, that's a spectator ion, and you're left with an H negative. You don't often see it, but it can happen. It's an H negative, anything negative wants to become neutral, right? How's that H going to become neutral? It's going to get a proton from somewhere. Where's it going to get that proton from? In this case, that hydrogen.
Okay, I think I understand. And then it gives the extra electrons to the O, but the O that wants to be neutral, and so it gives it to wherever it's the most positive, which is wherever the Br was.
Yeah, that Br will leave because that is the leaving group, right? So you have your alpha carbon here.
So is that saying that the hydrogen bonds to this carbon and also the other one, while also that carbon is bonded to, like in a triangular formation?
Correct. So when this folds in on itself here, over here, so when this oxygen, this alone pair, goes to one of the carbons of its own, that's where your bond is, right? Because it's no different than any other bond that we've made or created, right? So if you have OH, right, just hypothetically, if you have OH, right, and it's bonding with that H, that's where the bond is going to occur. Right?
Okay.
So that's what this dotted line is.
All right. Thank you.
No problem. All right. So everybody good? Cool on this?
Yeah. Is there any way you could scroll up just really quick to that one that you did before? I just wanted to take a quick screenshot of it. Oh, maybe it's not there anymore. Oh, yeah, that one right up there. Thank you. I just want to get it real quick. All right, got it.
Yeah, and if anybody wants to look at this, I'm actually streaming this on YouTube. So, So yeah, I guess I'll drop the link to the YouTube that I do have. I have all of my lectures from a previous semester. So fall and last summer and fall, I have my lectures recorded and on YouTube. So use a link to that always. So given that link, this is on it as well. All right, so you see how you have this nucleophile, right? This nucleophile, you have a leaving group, right? So something's going to happen first. That nucleophile, all right, it's just telling you the product and it's asking you how it happened. All right, so how can this happen? It's just like the one we did before, all right? These electrons, they're going to take one of these hydrogens, all right? So you're left with cool. All right. So now your leaving group is going to leave. All right. So that's going to be your alpha carbon. It's going to be your alpha carbon. All right, and you have your N with your electrons. All right, so what's going to happen? Again, alpha is just the plus sign. So that's where the bond is going to be made. That's why this ring occurs. All right. So leaving group is leaving by itself. So leaving groups leave regardless, all right? Of course, it depends on the strength of the leaving group, but if you have any kind of substitution reaction, the leaving group has to leave in order for a substitution to occur, just to begin with, all right? So any other question, comments, concerns on chapter 6?
Your YouTube channel does it have like this same worksheet of you going over it, or is it just going to be the recording of this?
So, I mean, does anybody have a YouTube channel, and does anybody know if I can put a file on YouTube? Okay, so that answers that. This is also one of the reasons why I'm putting the files in the chat. So I'll put this in the chat again. So this is week 6. Okay.
Excuse me.
Yeah.
I just want to say, like, I've seen like problems like this been done different way in like a tutoring session, but they got the same answer. So like the OH would attack the Br and then replace it, and then attack the H2. And so I wanted to know what you thought about that.
So the OH does not attack the Br. I don't know if he told you to do that, but the Br has to leave. The Br leaves and is a spectator ion in and of itself. All right, the Br leaves. Okay, now you're left with this. Okay. You can put the links in the description of the YouTube channel. Links to files. All right, so you have this. The Br leaves. All right. Now this OH is again going to remove a hydrogen from that. All right. So the OH does not attack the Br. All right. The nucleophiles do not attack the leaving group. All right. In general, the nucleophiles replace where the leaving group was. All right. This is this type of reaction, just like the one you saw in a quiz, is an intramolecular reaction. All right. So that OH isn't really the nucleophile in this case. Right. So that OH is deprotonating. Right. It's the same exact kind of mechanism as this one. All right, so someone's asking something in the chat. Oh, okay. It's because of resonance. All right, so these again are ranking just the leaving group for SN2. All right, so again, SN2s want what type of primary? I mean, what I just said, what type of primary? Well, what type of substrate? Primary. All right. What's even better than primary is a methyl. All right, so this is why this is number one. Number two, all right, 2 and 3 are 2 and 3 because of resonance. All right, similar to how you saw a phenol versus a benzol. That. All right, which one of these has more resonance? Left or the right? So, I mean, in these 1 here or 2 here, which one has more resonance?
Isn't it the first one?
Correct. All right. And the reason for that is because of the ring. All right. Again, if the leaving group is directly attached to the double bond, it will not occur. All right. This is another example of this. All right. This is a super no. All right. Never going to happen. All right. All it takes for it to become really good is becoming a benzyl. All right. Not a phenyl, but a benzyl.
I have a quick question for that one before. I'm sorry, but for that one before, when there's like multiple things going on like that, I guess it's just I'm having a little bit of difficulty of like knowing which way to go. So in this case, obviously we have the product, so it might be a little bit more straightforward, but I mean.
All right, so let's act as if the product's not there. Let's see, how can we do that? Where's this? I'm just text. No. So leaving group leaves. Right. All right. So what do we know from acid-base chemistry? All right. This OH is negative and wants to become what?
Neutral
How's it going to do that?
by attacking the hydrogen. I guess just ignore that the positive sign is there, because I guess it's just you automatically want to like think that it can go there, I guess. I don't know.
Yeah, so I get the rationale that you're saying. So this,
Like, I'm just trying to find a way to like separate stuff in my, like, compartmentalize so that I don't get confused.
yeah. So let me put it this way. If you, I guess a safe rule of thumb would be if you have a negatively charged OH or a negatively charged proton as a nucleophile, it's going to want to become neutral.
Okay, that's a good way. That I think will stick.
All right, so with this one, right, it doesn't, all it is it would just become the solvent.
Well, in this one, the other one, like there is an actual like extra proton, essentially, not necessarily, but you know what I mean, that it can actually take to become neutral, whereas in those other ones, it didn't have that like H, how the other N had the H, I guess. I don't know if that's a good way to look at it or not.
Yeah. So like with this one, right, you have this negatively charged oxygen, but if it were to take an oxygen, it would just become the solvent. And is that solvent a strong nucleophile?
No.
So when that becomes water by taking that hydrogen, it becomes water, it becomes a weak nucleophile, so it's not going to be the thing that's attacking and replacing the leaving group.
Okay, that makes sense.
Ashley, does that also answer your question as I was talking more about it?
Yeah, it was that like one statement that I was trying to get again that you said that.
So like, yeah, so like acid-base chemistry, if you have an OH, if you have an OH, losing it. All right, if you have an OH and you have a negatively charged hydrogen, like that quiz example you saw, all right, if there is a protonated thing that you can deprotonate, it's gonna. All right, because once it does that, it's no longer a strong nucleophile, and IE isn't going to replace the leaving group.
That totally makes sense.
You said what? Was it going to replace the leaving group again? Sorry. I'm sorry. I was trying to write, but I'm not as fast as you're speaking.
So like, again, so like this OH, right?
Yeah, I got that.
So it's negatively charged. One way it can become neutral is by replacing the leaving group, right? But it has the ability to become water.
Okay.
And it's going to want to do that because oxygen is electronegative. It's super negative. It wants to become neutral. It wants to become stable.
Mm-hmm.
Right? So it's going to remove this hydrogen here because it's able to, right? That then becomes water. So if you just have water, is water a strong nucleophile?
No.
No. So this isn't going to be what replaces that BR.
Okay, that makes sense.
All right. Sorry. So yeah, I've more recently, I think at 8:42, I put both sheets that I have for chapter 6 on in the chat. All right. question, comments, concerns? Because I am now almost 2.5 hours deep.
Thank you for doing this on a Saturday night.
Yeah,
No
thanks.
problem.
Yes, thank you.
No problem. Any question, comments, concerns? So we went over mainly chapter 4. A lot of chapter 4 we didn't had to go. We did conversion of Newman and bond line. We went over differentiating stability with gauche, anti, and partial eclipse, full eclipse. If you guys know how to RNS, if anybody needs me to go over a couple examples of RNS, tell me before I do click end. But let me tell you right now, if you can RNS successfully over and over, you're very good for chapter 5. Because again, I'm assuming that there is some people here that aren't necessarily mine. So I do see some unrecognizable names. So comparing an answer, finding out whether something's in an enantiomer or diastereomer, RNS it. All right, I'm sure you guys will see this problem. Maybe not exactly the exact molecular atoms, but you will see this kind of problem. Guaranteed. All right. We'll ask you what's the configurations, or he's going to ask you more likely what's the relationship between them, i.e., are they enantiomers or diastereomers? All right. And I can tell you right now, the easiest way you can do that is RNS it. All right. Now, does anybody know the rule of thumb that we use when we find RNS? So after we find RNS, does anybody know that rule of thumb in order to distinguish between enantiomer and diastereomers?
Isn't it if they like stay the same or if they're opposite when you compare the two? I'm like blanking right now.
So even if you could have 2, you could have 5. All right. So say this is molecule A, say this is molecule B. I didn't do the RNS of this because I'm not going to go through it, because I'm going to assume that you guys know how to find RNS. But if you have first carbon is R, second carbon is S. In molecule B, you have S, and then you have R. All right. Did all of the chiral centers change?
Yes.
Yes. So they are enantiomers. All right. Keyword all. If all of them changed, they're enantiomers. So it could be 2, it could be 5. If all of them changed configuration, i.e. the letter of RNS, then it's enantiomers. If not all of them, but some of them, then they are no longer enantiomers, they're diastereomers. All right. All it takes is 1. All right. Also, if you guys get something like this that only has 1 chiral center, diastereomers is not a correct option. All right. You have to have 2 chiral centers to even be considered as a diastereomer. All right.
Did you say the some chiral centers change one again? I didn't hear it.
Yep. So it's the key word is all or not all. If all letters change from version A to version B, all right, then it's an enantiomer. If not all, but some of them, all it takes is 1. All right. If there's 5 chiral centers and 4 of them change, but except 1 of them, all it takes is 1. If not all of them, but some of them change, then it's diastereomer.
Got it. Thank you.
All right. And again, if you have something with only 1 chiral center, it cannot exist as a diastereomer. You have to have 2 chiral centers in a molecule to even be considered to have another version as a diastereomer. All right. So somebody asked if there's going to be Fisher. Does anybody want me to go over Fisher just in case? So Fisher, you can easily do this. Okay, so I like to do arms versus head and legs. All right, or a dog or a cat. If you have a dog or a cat, all right, the things that are pointing out to the side are its legs. All right, and they are wedged. All right, and the head and tail of the cat and dog are dashed. Cool. All right. So now prioritize. All right, so given this one here, I'll do in red, that chiral center, what's our first priority? First priority coming off of that red carbon. Let's see. I like to personally find my highest and lowest. What's our lowest priority? Hydrogen. All right, now what's second in line from number one? Is it the methyl or the group below? Second priority. Is it methyl on top or the group below? It is the group below. Does anybody need me to explain why? All right, Cooper. So you have a carbon with 3 hydrogens. And you have a carbon with another carbon and a bromine. Which one's bigger? Which one has a higher overall atomic number? Top or bottom? The top, the bottom one. All right, so 2. This would be 3. All right, so so after you do the 3D, all right, so arms. So the arms of your dog or cat is wedged. The top and bottom thing, the head and the tail are dashed. All right, after you find after you find your priorities, you don't have to ignore anything. All right, you do not have to ignore anything. All right, you simply find your rotation. 1, 2, 3, 4. What is this rotation looking like right now? R or S right now, based on the arrow I just drew? R. Now the little caveat, the only thing you'd have to remember is if your lowest priority, 4, is on an arm, flip. All right. So is 4 on an arm? Where's our 4th priority, a head and tail? 4 is on an arm, so we flip. That's all you need to know for Fisher. Right. Also, Natalie brings up clockwise. I personally never liked clockwise and counterclockwise. I'm pretty sure we've all driven before. I don't know if I'm doing it the way I don't know what your perspective is, but if you're turning the steering wheel to the right, it's R. All right. If you're turning left, then it's S. All right. Cool. That's just me personally. I never like to think of a clock. All right. Also, somebody brought it up in tutoring, and I brought it up because it came up on, again, a former quiz before. So I'm pretty sure you've either seen one or both of these on your Chapter 5 quiz. I'm just going to tell you right now. This one's the one that's got it. All right. I'm sure there's a rule of thumb out there, and there is geometrical orbital reasons for that. You don't have to understand it. All right. Just know that if you're comparing A to B, A is the one that's chiral. All right. And if you want to look into it, it's called an alene.
What was the rule for that? It was just if it has an even number of double bonds, it's chiral. Odd number, it's achiral. They gave us some rule, but I've heard a couple different things, so now I'm kind of confused on how they did it.
Is anybody in here, has anybody heard that rule before? I'm going to put something in the chat right now that explains it. All right, so.
And obviously you want to make sure that the carbon has two different like groups. Obviously it can't have the same of the two, but if it was a certain number of double bonds with two different groups on those carbons or whatever, however many groups it's got on it, that it was chiral, and then odd number achiral, if I don't have it backwards.
So obviously this is better handwriting than my mouse work. I don't have a tablet, but I'm putting something in the chat right now that is all you need to know for alenes. All right. Also, somebody was confused before. He can ask you. He can ask you in a what is chiral by not asking you what's chiral. All right. So on this handout, I will put it in the chat. This handout, week 5, which means just chapter 5. All right. And something else I have for chapter 5. All right. If he asks you if something is capable of existing as an enantiomer, he's asking you if it's chiral. If he asks you, is it capable of rotating polarized light, he's asking you if it's chiral. Okay? That all of that just ties back to if the molecule is chiral. All right. Are meso compounds chiral?
No, not overall.
Can meso compounds rotate light?
No.
Can meso compounds exist as an enantiomer?
No.
No.
I don't think so.
Cool. All right. Now, this I've seen on an exam or on a quiz before. So in case you've seen it or are going to see it, I'm just going to put X as a halogen or another group. All right, this is a meso compound. I'm just going to put it out there. All right. Why? Can somebody tell me why?
The internal plane of symmetry, and then the chiral centers will cancel one another out.
Correct. Cool. All right, so all it would take in order to make this chiral, or make this capable of existing as an enantiomer, or another way you could put it is capable of rotating light, is simply making one of these as dashed. All right, but if you were to make one of these dashed, then it no longer has a internal plane of symmetry, i.e. would not be meso. All right, cool. And Farah, again, he can ask you, he's going to ask you about which of the following molecules is chiral. All right, but just in case, all of that means is, again, chiral molecules rotate light and they can have enantiomers, right? So he could ask you which one of these is capable of rotating light and which one of these can be an enantiomer. All of that means, and all that is asking, is which one of these molecules is chiral. Cool.
And let me ask you one thing. If it boils down to time, because one thing is, I'm sure you probably know, you've taken this class before, that the end of chapter problems can be very time consuming. If you would suggest preparing for the exam, if it came down to handouts versus end of chapter problems versus exam reviews, what would you say to focus our energy on the most?
So by exam reviews, what do you mean? Like what I'm doing now?
Yeah, like we have SI handouts for the exam review, for example.
So I have a feeling that the exam reviews for SI is kind of a compilation of the chapter handout. And when I took this course, the exam reviews in the SI were simply going over the SI handouts for each chapter. So what I can say with regard to SI and how I went through this course is this again, you're wasting lots of time, energy, and ink or pencil if you're just taking hours to go and take notes throughout the chapter. All right.
Oh, I
He's
stopped
not
doing
going
it
to ask.
a long time ago.
Yeah, he's not going to ask you, any of you guys, what the definition of something is. All right. He's going to want to. He's assuming you already know and is asking you to apply it to these solving problems, i.e. solving problems, keyword solving problems. All right. So how I did it and how I preach is SI handouts to help you answer the end of chapter problems. Answer the end of chapter problems, work on them. All right. And if you have problems with the end of chapter problems, take them to OC squared or your TA. All right. And that's every week. All right. A chapter per week. All right. Because as you can tell, the exams are 3 chapters. If you do a chapter per week, then that leaves you with about a week or so, 4 to 7 days a week or so to cover everything you need as an overall review.
Okay, makes sense.
And if you can smoothly get through the end of chapter problems, then you're pretty set. But I know what you're saying, because the end of chapter problems can be lengthy and time consuming. I can tell you right now, there are chapters, some of them coming up, to where half the problems were irrelevant to the exams when I took the course.
Yeah, that's the thing, is that I don't want to waste time on doing like drawing 16 isomers of C4H8 or whatever, because we're not going to be asked to draw 16 isomers on the exam. So
Correct. Yeah. Yeah, but the fact that you are your second exam in, you know how he asks questions, right? And in particular, Roche. Let me pull up Roche's bullshit. Don't worry, Roche is a great guy. He really is. He's just hard to understand sometimes. Let me pull this up. New share. All right, so for example, this is a good question. This is a good question. This is a good question. What's the answer to this one? We went over it.
Spyro.
Spyro. All right. Now, that, again, we went over that. Now, chairs. So the different types of chairs, I'll tell you right now, the chair is always the most stable. All right. Now, A is called a boat, and C is called a twist boat. So I'll put it in the chat right now in terms of ranking of stability. Chair is best. So chair, then twist boat, then a boat, then a half.
Can I just ask you, so when we're doing the chair flip, because I'm looking back at my notes and I don't know, I don't know if it's been a little while. I don't really understand my notes right now. But when we're doing one, say if you have the chair, right? Or let's just look at that chair right there. And the left corner, let's just say that is 1. And the other 1, 2, 3, 4. The other corner's 4. If you do the flip and the right corner comes up and the left corner goes down, do you also reverse the numbers, meaning that the other one would end up being 4 and then the other one would end up being 1?
Let me just go ahead and put this. Catch it faster than it disappears. All right. So just so I can draw. So I can draw in PDF. All right. So which one are you saying is carbon 1?
So say that like for B, the chair, the top left corner is number 1. Because what Chris did is I think he did some like trick in one of his sessions where he just goes, always make this one 1. And then you can just, I think he said you can just move it over 1 and it's kind of the same thing, but I don't want to go off that in case I misunderstood him.
I would propose to, because carbon number 1 isn't always going to be that carbon.
Yeah.
So I would propose do the chair flip itself.
Okay.
So, again, it's literally a reason why it's called a chair is because it literally looks like a lawn chair. So a chair flip is your cousin, brother, whatever, comes out, kicks that lever out from under you, and your head goes flying down. So that carbon comes down, this carbon comes up, and you end up as that line.
Are you drawing something or are you just, I don't see it. Oh, okay, there we go.
All right, so if this carbon is what came down and that was carbon number 1, then that means this carbon is number 1.
Okay, so we do keep, yeah, okay. That's what I thought before. I just wasn't sure if, because I know that the one went up and then the other one went down. I just didn't know if the actual numbers needed to change at all.
Yeah, that would not become carbon number 2. All right, that's why I personally, if I'm going to pick something ambiguously, I'd stay consistent with my numbers.
Okay.
So given that this carbon came down, that means this carbon is your number 1 if you labeled that carbon number 1 before. That does not mean that this carbon is number 1, just because both are pointing in an upward direction. All right.
Okay. So if that one was 1, that one's 4. So then basically just you can just go the opposite direction, put the 1 going down and the 4 going up and then fill.
Yeah, so 1, 2, 3, 4. You could also count, right? So if this carbon is number 1, move to the right one, that's 2, move to the right one, that's 3. If this is your carbon number 1, move to the right one, that's 2, move to the right one, that's 3, move to the right one, 4.
Okay, thank you for clarifying that, because like I said, I was looking at my notes and I couldn't understand them.
Yeah. All right. Forgot what I was saying before. No. Oh yeah, I was explaining how sometimes Roche's stuff isn't that great. Here's a perfect example of why. Problem 11, you're not going to see on the exam because that's exam 1. Right. This was exam 1. That's chapter 3. All right. And this is too complicated of a structure. I've never, okay, in my defense, Lepore hasn't taught for over 2 years. He taught when I was a sophomore and I'm graduating in April. All right. So he hasn't taught forever. So Lepore, us TAs know not as much about, although I actually did take Lepore's class. and he is more experimentalist, and he is more a little bit nuanced than Jermaine. Jermaine, I can tell you right now, you're not going to see. You're very likely. I'm 95% sure if you're taking Jermaine, you're not going to see a substrate that looks like this. All right. But even if you do, run through that table, run through the rationale. What classification is the substrate? Primary, secondary, tertiary. If it's secondary, then look at the nucleophiles, the strong or weak. All right. I'm pretty sure they said use the same tests. I doubt it. They work together, and he and Jermaine actually is one of the postdocs in Lepore's lab and group. But whether or not they use the same exact tests, I doubt it. But the different sections of Germain, so if you're in section 1 or section 2 versus in Germain, they are the same test, but probably likely a different order or version. But again, Lepore hasn't taught for 2 years, full years, not 2 semesters, but 2 full years. So 6 semesters. He's likely, again, as you can tell, in the past 2 years, you've never had to been required to participate in lecture, and Lepore for some reason does that. So he is a little bit weird. He's a little bit awkward, as you can tell, but he gets a little twinkle in his eye when it comes to organic chemistry. So yeah, Lepore sent this to you guys, and again, that's both of these. That's chapter 1. This is chapter 3. Again, so this is classic. This is classic Roche, but I will put the review this exact answer key in the chat as well. Yeah, he's very nice. He's kind of like the organic chemistry of Hutchell. Very nice, but you have to get in his face in order for him to hear you. All right. So we're about three hours in, and I'm about done. So is my voice. Yeah. All right. So any question, comments, concerns specifically? All right. And if you need to reach me, I'm just putting this in. This is my signature for my email. If you need to reach me, that's me. All right. So if there are any question, comments, concerns, find me, contact me for some reason, but I do gotta head. All right. Thank you, you too.